Hello everyone. My name is Janardhan Chejarla, and in this talk, I'm going to talk about high frequency trading where speed is everything. We are tackling a big problem. How do you keep things secure when you have to be faster than lightning? And if we add security tools, they basically slow down the trading. We need a new way to be both fast and at the same time safe. Think of three main goals in trading. One is speed, scale, where you have to process millions of orders per second, and at the same time, you cannot compromise security. Usually, when you focus on one thing, it could turn into sacrificing the other thing. The main issue is that the latency tax. Every security check adds a delay. If a traditional firewall adds, let's say, 50 microseconds, we're going to lose some money, right? We have to design systems that handle huge volume without getting slow. So that's the objective. So here comes the event-driven and cloud-native architecture where you can design the systems without compromising the points that we just talked about. So let's talk about the latency killer. Why is a standard computer is too slow? Because the operating systems, for example, you look at Linux or Windows, gets in the way of the network card. We use specialized tools, DPDK or RDMA, to skip the OS entirely and talk straight to the network card. So this gives us the pure speed, but it also means we bypass some of the security measures. We must move securely to the hardware itself. We use the concept of ARN, which will give a sub-microsecond latency. So for the absolute fastest part of the system, that which is the order matching system, we use the messaging system called ARN. ARN is like extremely reliable, encrypted instant messaging for machines. It's built for speed and uses a method called raft consensus to ensure all our trading computers agree on the order of the trade, even if one computer breaks. So let's talk about cloud native event bus and orchestration. For slower and high volume tasks like analyzing market data or settling trades, we use tools like Kafka. This allows us to handle huge systems of information without slowing down the trading engine. We separate the tasks. One part handles the trade, which has to be very fast, and another handles record keeping, for example, which could be high volume. It not necessarily to be like ultra fast. It still should handle huge volume. So the latency tax, let's look at some of these security patterns and how each of them will add security latency in terms of like microseconds. So this chart will show how much delay common security tools will add. A common security pattern called a sidecar used in modern microservices adds about 150 microseconds. That's too much for high frequency trading. We must bake security directly into the application code using in-process library to keep the delay to 5 microseconds or even less. So at the same time, when we talk about all these high frequency tradings and a bunch of other applications connected to that, observability is also one of the key aspects of the system. And at the same time, we have to achieve this observability without much penalty. If you can't use the standard security tools, so how do we watch what's happening? We use a tool called eBPF, which lets us hook directly into the kernel without adding a delay. It lets us observe every packet and every action of the system that it takes for compliance, all while maintaining zero latency goal. It's observation without the performance penalty. So that is the goal basically. Determinism itself is the security, event sourcing. So anything that is happening in the system, we need to capture that as an immutable event. If you can't replay, basically, if you have to replay a scenario, if something happened in the system, these immutable events are very helpful. You can basically replay the event, what happened in the past. And if you can't replay it, you can't prove it, what happened, right? That's the key. Okay. And forensics, like for example, if something happened in the system or something went wrong, you should be able to do the post-mortem analysis where you need to replay the trading sequence, what exactly happened at a certain time interval. And compliance is another aspect. So Nowadays, regulators are demanding proof of best execution, and deterministic logs provide the evidence of the system behavior. So, you know, let's talk about compliance as a code and real world scale. By building security and resilience into the architecture, we're calling it as a compliance as a code, we get some amazing results. For example, if you look at some of these real world examples, the London Stock Exchange can handle almost like close to 15 million messages per second, and they cut out the system's downtime from 40 hours to just about 2.5 years in the whole year. This shows that the speed and reliability goes hand in hand. And in short, when you talk about resilience and chaos engineering, basically in a high frequency trading system, a system that cannot recover in milliseconds is a system that already failed. You can think of it as a quote, but so that's the core principle of the high frequency trading system. And not only what we talked in this talk, there is also a future aspect of the high frequency trading systems. There is still a lot need to be improved. The next frontier is moving security logic directly into the hardware, and we need to achieve zero CPU overhead. We need to implement the firewalls, risk checks, and encryption directly into the FPGA gates and bump in the wire. Bad packets are dropped at the core level, ensuring that they never consume the whole CPU. And of course, we need to implement all these things with the aspect of public clouds, not only private clouds, public clouds as well. That's the end of this talk. Thank you for attending.